we got Larry, Moe, and Curly. You know, those three doofuses from the old television program. And Larry, Moe, and Curly are going to push a big crate across some ice. Now this is kind of a bird's eye view. We're looking down at Larry, Moe, and Curly, and they're all going to push the block to the right. We're making it sort of a bird's eye view down on the ice, so we only have to worry about one dimension here. We're just going to worry about X. X is to the right and positive, as usual. Okay, so everything we're doing here, in the last video we talked some about X and Y. This is going to be a simple one-dimensional case, and then it looks like over the next couple of videos we're going to bring the Y dimension back in. Okay, so all we have to think about for Newton's second law here is the sum of the forces in the X direction is M times A in the X direction. Okay. So, we have three forces, L, M, and C, Larry, Moe, and Curly, and each of these gentlemen are pushing the crate across the ice to the right with a force of 80 newtons. Each one of them is pushing with 80 newtons. What we want to know is two things. What's the acceleration of the crate, and how long does it take for the crate to go 25 meters, assuming that we start from rest. Okay, so they're starting from rest. They're all going to push on the crate that way with a force of 80 newtons. And it's on the ice. And the only reason I put it on ice is because we're not worrying about friction here. Not till chapter 6 does friction come in. So there's two things. We want to know what the acceleration of the block of the crate is, and how long it takes to go 25 meters, given that it starts from rest. Okay. So once again, let's bring our Newton's second law up here. Sum of the forces, X direction is M times A sub X. And of course, when I ask for the acceleration, because all the forces are in the X direction, the acceleration is going to be in the X direction also. Okay. So maybe I can write this here. Maybe this would A equals A sub X equals what? Because all the acceleration is in the direction of the forces. It'll be to the right. It'll be in the positive X direction, right? We're not going to push on the crate this direction and have it go that way. That's not going to happen, right? It's going to go in the same direction we're pushing it. Starting from rest. Okay. So, what is the sum of the forces? Well, the sum of the forces in the X direction is simply L plus M plus C. There are three forces in the X direction. They are all positive, and that's going to equal M times A. And I can drop the subscript X now because A is equal to A sub X. So might as well just not worry about specifying. We know it's in the X direction. Okay. So I'm going to put some numbers in here. I'm not going to do it algebraically. I'm going to put numbers in. So this is going to be 80 newtons plus 80 newtons plus 80 newtons, right? They're all positive. They're all 80 newtons. So this is the sum of the forces, is 1,000 kilograms times A. Okay, so the sum of the forces is 240 newtons. That is sigma F sub X. Okay, so you start with sigma F and you unpack it and you figure all the forces going on and you put them in there. And there are 3 80 Newton forces all to the right. And so that is going to equal 1,000 kilograms times A. And you can solve this for A. A is 240 newtons over 1,000 kilograms, belongs in the denominator. Equals 0.24 meters per second squared. That is the acceleration. Okay. Simple application of Newton's second law. Now, so A sub x, A is equal to 0.24 meters per second squared. And if we want to draw it in full-blown vector form, we'd say A is 0.24 meters per second squared in the x direction, x hat, like that. That's how we would write it in full-blown vector form right there. Now, how long does it take to go 25 meters, given from rest? How do you think we're going to do this, y'all? How do we think we're going to do this? Equations of motion from before. Number 2, x equals x naught plus v naught t plus 1/2 at squared. Squeak, squeak, squeak. If we say that we start at x equals 0, that'll go to 0. V naught, starting from rest, 0. And so we can solve this for t. And t equals 2x for a. In other words, just because we've started a whole new section doesn't mean that we that we forget what we learned before. Does not happen. It's like math. It builds on itself. So you'll be using these equations of motion throughout the semester and into next semester also. They're not going to go away. So time is 2 times 25 meters over the acceleration, which is 0.24 meters per second squared. And this equals what? 14 seconds. That's how long it takes to go 25 meters, starting from rest, with Larry, Mo, and Curly each pushing the block with a force of 80 newtons. So the answer here is 14 seconds. Okay. All right, now let's change it up a little bit. Okay. I'm going to leave this up top. We're going to change the situation just a little bit. We have time to do this. We totally have time to do this. Now that you've seen how I've done it once, I'm going to change the situation a little bit, and you'll see how things are going to change up here. This board's actually gives me a good workout erasing this thing. It's pretty tough to erase. You got to really press pretty hard on this glass. But it is done. All right, so now what's going to happen is we're going to have a little bit of a change. Curly is going to turn around to this side. It's still ice. I just happen to be erasing that. Curly is going to come around and press from this direction now. And we're going to ask the same questions. What's the acceleration? And how long does it take to go 25 meters? Okay. Now, the magnitudes of the forces are going to be the same. Okay. That is, Larry and Moe still going to be 80 newtons. But now Curly, semicolon, Curly now is going to have a force not of 80 newtons, but of, get ready for it, negative 80 newtons, because he's now pushing that way. Negative 80 newtons. Now Curly's working against them. Okay? So now what do we have for the sum of the forces? Now we're going to have L plus M, Larry and Moe, minus Curly. We have two positive forces and one negative force. So the sum of the forces now is not L plus M plus C, it's L plus M minus C. That's still the sum of our forces, but it's going to have a different value now. Equals the mass times the acceleration. So now the sum of the forces is not 80 plus 80 plus 80, it is 80 plus 80 minus 80 is the mass 1,000 kilograms times A. This is how the left-hand side of this equation works. You have to add up the forces. Forces are vectors. Vectors have direction, so you need to think about direction when you add them up. And assign the signs, SIG and S's, appropriately. So now what we have is we have 80 plus 80 minus 80 gives you 80 newtons. Now the sum of the forces is 80 newtons, and that equals 1,000 kilograms. By the way, 1,000 kilograms is known as a metric ton times A. So A now is 80 newtons over 1,000 kilograms, which equals 0.08 meters per second squared. So now, now we have a much smaller acceleration. So will it take less time or more time to go the 25 meters? Because now the acceleration is so much less. In fact, it's 1/3. Okay? The acceleration is 1/3. So now will it take more time or less time to get at that 25 meters? It'll take more time. And you'll do your math the same way. You're going to still use x equals x naught plus v naught t plus 1/2 at squared. These things are still going to be 0. Starting line is still 0. Initial velocity is still 0. But when you solve this for time, you're going to get t is 24 seconds. Okay. With Curly working against them, like the stooge he is, there's going to be less acceleration, which means it'll take more time. So notice the force in this case was 1/3 of the previous force. The acceleration is 1/3, right? Because 0.08 is 1/3 of 0.24 is 1/3, but the time is not larger by a factor of 3. It's because of this square root. I mean, it's because of this square business right there. Okay. So the force and acceleration are proportional, right? If we cut the force down to 1/3 of its original value, when Curly came back around to push that way, we cut the force down to 1/3 of its original value, and the acceleration also went down by 1/3 of its original value to 1/3 of its original value, but the time did not increase by a factor of 3. And that's because of this square in the equation there. Okay? Next up, let's see, we're going to talk about Newton's third law, and then we're going to put it, boom, all together.